So I am here today to talk about the 15 years of real-time stability data that we have now at room temperature, and also a bit about accelerated aging, but it will be dealt after by Dave also. So DNA data storage, we all are here, we know it will contribute to resolve the data volume explosion crisis. But there are a lot of parameters to take into account, and also a lot of challenges to address, like the scale of storage, information density, but also DNA stability and data retrieval, because stability, surprisingly, is often overlooked. So I will present today really quickly, because it's already been done, it will be done later also, the degradation mechanisms, the solution that we developed 20 years ago, and how we evaluate the stability of DNA in these conditions. So the main main mechanisms of degradations, they come from water. It's really the main agent. And all of these modifications and breakings will lead to chain break. That's what we monitor. The consequence is that so we have chain breakage, and it's really the water content that will contribute to the damage of DNA. And the relative importance of hydrolysis and oxidation will strongly vary according to the water content, and less by the environment parameters. And for synthetic DNA, it's not a big parameter. So we need to protect DNA from water. But at the beginning of the company, a lot of time ago, we didn't know how hermetic were the containers or the sealings that were on the market. So we evaluated different containers and closures, like crimped vials, O-ring tubes, and regular plastic tubes. And we put 1 gram of a desiccant inside each container, and we measured the water uptake during time. And the results were counterintuitive. The more developed were the closures, the more advanced they were, the more water was entering the containers. So we were not able to find any container that would really prevent water from coming back to dehydrated DNA. That's why we developed a new container at that time. So this is briefly the technology that we developed. It's a metallic capsule. Inside it, we have a glass vial, and we deposit the molecules in solution, and then we dry them, and we close the container with also a cap in stainless steel, and we laser seal this under argon that is completely dried, so without moisture, without oxygen, so that the DNA or RNA are always under argon throughout the whole life. So at the beginning, we were targeting biobanking market, molecular diagnostics, and more recently, DNA data storage. We have been able, throughout the years, to monitor the stability of the molecules inside these containers. And we developed 3 different ways of doing the monitoring of chain breakage. The first molecule that we used is supercode plasmid DNA, because in this supercode form, you only need one break on one of the 2 strands to go to the open circle form. And it's really practical to see, to distinguish them on a simple gel, so it's really easy. And with that, we can monitor the chain breakage rate here, the number of breaks per nucleotide per second, and it's really sensitive. The second way of monitoring chain breakage is by using genomic DNA, because we were in the biobanking world. So you have high molecular weight DNA here. It's more than 20 kb. You denature it so that you separate the 2 strands, and you measure the maximum size with the maximum intensity. And you have a relationship between L max and the degradation rate of the molecules because you know the time they were stored. And also, we have a third way of doing monitoring with qPCR and digital PCR, but I won't develop here. So at the beginning, we knew we developed a good solution and that it will be very long to evaluate the stability at room temperature. So we started with accelerated aging. I won't go into detail because it will be developed in the next talk by Dave, but it's based on the Arrhenius model. And we published a lot on this. We were the first to publish the Arrhenius equation for DNA in the solid state. Then we developed the process for RNA, so we also published an Arrhenius equation for RNA and also for DNA inside biospecimens that are encapsulated. So after these validations, we also wanted to have a long-term evaluation, but at room temperature, to evaluate the real degradation rate at room temperature. And we have different objectives. The first one is to verify that accelerated aging is really accurate, that the Arrhenius equation can be used, and also to take potential unforeseen parameters or factors into account to be sure that in real life we will have the same performance. We also published some papers. So here I will show you a study that we started 15 years ago. And the objective, the first objective was to generalize the use of the capsules for a lot of different materials, because in the biobanking, you never know what you will have to store. So we collected a lot of different biospecimens, cell lines, bacteria, tissues, saliva, plants, and we extracted DNA and RNA with different extraction methods because we wanted to verify that these methods will lead to the same stability of the molecules. We also developed a process to store DNA and RNA that are still inside the biospecimen, so that you avoid the extraction step, again, for biobanking. So we collected everything, we extracted, we stabilized in the capsule, and then we performed accelerated aging. We performed Arrhenius equations on all of these, and we simulated after that 25 to 100 years of storage at room temperature, and we saw no degradation. And I don't show you these results. But we also kept capsules and controls at that time, and that we kept for up to 15 years. So we have capsules that were stored at room temperature without any moisture or temperature control. So it varied between 15 to 30 degrees in the lab. We kept control capsules at -20. And also, of course, the controls in solution stored at -20 or -80 DNA and RNA in solution. And after these years, up to 15 years, we opened the mini capsules, we rehydrated the molecules, and extracted DNA and RNA when needed, and we performed the analysis. So these are an extract of the results. So for genomic DNA, I selected the samples that gave different results, but in the end, it's all the same. We can compare every time the capsule and the control in -20, and we don't see any size difference after for more than 14 years. If we have more than 20 kb here, to high molecular weight DNA, we can calculate from the model that I showed you earlier that it corresponds to a degradation rate less than this value here. So because it's still high molecular weight. With plasmid DNA, we conducted this experiment at room temperature for 8 months, and we published this. And we compared different conditions. At that time, we compared the capsule with DNA that was dried inside plastic tubes, either with just buffer, or with a Trielo's matrix, or a commercial matrix. And we measured the supercoil content throughout time for 8 months. Without any matrix, DNA is impossible to recover because it aggregates. You lose all your molecules very quickly because it's exposed to atmosphere, and it's water that does the aggregation acceleration. And with the matrix, you recover all the DNA, but it degrades rapidly. And we continued this kinetic at room temperature. And now we have 15 years of data. And this is the result here. So we're still very high in terms of supercoil content. And we can calculate the degradation rate at room temperature with this kinetic here. So we are approximately here. This number doesn't mean anything, so I will show you on an Arrhenius scale what it means. So here is the last Arrhenius equation that we published in PLOS recently. It was measured by qPCR with 2 sides of targets, and we extrapolated the degradation rate at room temperature here. And here I put the numbers that we calculated from the long-term stability study at room temperature. In green, you have the rate that we calculated with plasmid DNA. So it's an actual rate. And here in orange, you have the maximum log because DNA is still high molecular weight after this time. So they are really grouped around the extrapolated value from the Arrhenius equation, so we can sort of validate that accelerated aging gives good results, and really we are in the same conditions in room temperature in the capsules. And as a comparison, here you have the degradation rate for DNA that has been dried, but which is not protected from the atmosphere. And you have 3 logs of difference in degradation rate. So when you are in the capsules, completely protected from water, it's 1,000 times less prone to degradation than without protection. I will also show you quickly what we have with RNA, because we know RNA is also a molecule that is really unstable. So here you have the results after 15 years, up to 15 years of total RNA inside the capsule. So we are really, really glad with these results, because we produce controls for molecular diagnostics that are based on RNA. So we can produce very large batches that will last a long time. And finally, we also analyzed DNA and RNA inside the biospecimen that were encapsulated, and we also have very good stabilities. So in conclusion, the capsules, DNAshell, RNAshell, really are the most advanced available technology now for DNA RNA stabilization at room temperature, and we have now 15 years of recorded performance. It's interesting because we need to build confidence in DNA data storage for the market, for the end users, and so now this data exists. But it's really imperative to use validated methods, to use all the controls, and to use also high sensitive methods really to demonstrate the stability, because it's really easy to hide a poor performance of a process. We see that all the time. So really we need to be in a standard community to share the results and to be sure that the results are good. Thank you.
Thanks very much for the very nice insight. Any questions? This. As long as everybody's thinking about questions, I have one. We see sometimes that the decay depends on the amount of DNA, especially in, let's say, plastic tubes. Let's say the less DNA we have, the faster it decays. Do you also see that? And is that circumvented if you go to your capsules?
We don't see that in the capsules. We really are able to store very low amounts and we recover everything, because I think that water and the aggregation will occur in the molecules, but also with the tube walls. And for RNA, also it's a problem because you have like a lyophilization inside the -80 freezers, and you can lose everything. Just
yeah, and you see that in the plastic comparative samples. You see that, but not in your.
Yes, exactly.
Yeah,
yes.
that. Yeah.
And also in solution, we kept also controlled in solution from the different biospecimen that we extracted. For some of them in solution, we see that we have a strong degradation at 4 degrees, and it's not happening in the capsules.
Yeah, I think in solution we also looked at contaminants, so metal ions in the water, which is really problematic even at low temperature, which of course you circumvent when it's dry and there's no water.
Exactly.
Yeah. Yeah, question there.
Thank you, very nice presentations. I was wondering, because you tested different processes for extractions, does it impact the DNA and also the aging after that? Because if any residues or, do you see any impacts?
So we can see impacts in solution. You have modified spectrums of absorbance, but in the end, in the capsule, we were able to show that there is no tendency coming from the extraction method or the biospecimen we use. The fact that you dry completely and you stay dried, it blocks everything that could happen in presence of water. But when you rehydrate, then you have to be careful, of course.
There was another question back there somewhere. 2 even.
Hi, thank you for the presentation. I just have a question. You talked about temperature. Do you plan to test the capsules also towards radiation and other means of degradation of the DNA molecules?
Yes, we plan to do that. In Prague meeting 2 weeks ago, I met some people that are specialized in radiation. But I also know that we have already some capsules that will be sent to space, for example. So we don't always know what our customers will do with the capsules, but we would like to launch this kind of study. Yeah.
And another question back there.
Hello, with the commercial trustworthiness piece that you spoke about at the end, is all this research being done in-house, or are you doing third-party verification now, or is that on the horizon?
For a lot of this work has been done in-house because we were early in the market at the beginning, and we had the first grant for building the company. Then the market was not here, so we worked a lot to prove that our initial instinct on the technology was the right one, so we really needed to publish a lot, so it was mostly in-house. But we also had some grants to work on specific aspects of the technology. For example, for the stabilization on live bacteria and viruses. So we worked with the army, the French army, with that, and Institut Pasteur. And more recently on DNA data storage, yes, we've been invited by Biosystemica to join them in the consortium for the Pearl DNA project.
And there's also with Microsoft, I think, data that's independent of your there's a paper where they compare different
Completely independent.
Completely independent.
Yeah, Lee contacted me to be included
so
in
there is really independent data
Yeah.
On DNA data storage
Exactly, yeah.
using this
Oh
technology.
yes, in-house, but also validated by a lot of partners and customers. We try to be evaluated independently.
There was another question in the middle here, perhaps.
Thank you. So we have the first online question. So about the cost of the technology. So the question is there any cost advantage with this technology over others' technology?
So for DNA data storage, it's
probably, yeah. Maybe I can ask the person to rephrase the question.
It's too soon for this market, I think, because we come from another market, and for biobanking, molecular diagnostics, we know that it's you start to I don't know how to say it in English. It doesn't cut. It has a cost at the beginning, but after 5 years, you are earning money. You are gaining money compared to the freezers, because freezers are still the reference. In biobanking and molecular diagnostics. But for DNA data storage, I think it's too soon because a lot of different processes will be launched, tested, evaluated, because there are a lot of aspects in the storage that are not addressed. But for cold storage, for cold data, really it's no-brainer. You store, you don't look at them, and you're sure that you will recover after more than 100 years, 1,000 years.
Thank you.
Any other questions? Yeah, there's one there. I think we have a little time. Yeah, there was a question there.
Just quickly, is the study still ongoing? Do you have more samples to be read in another 15 years?
We have more.
Okay, thank you.
And I really would like to thank my team, because they are really good at keeping this track of all these capsules and samples through the years. We are a very strong team that is here for a long time now, so I thank them for that.
With that, let's thank Marthe again. Thanks very much.